Hey everyone, welcome to the lecture for 3.2 on domain and range. So this is a continuation of our SLO FCN1. We want to be able to say, I can determine if a given relationship represents a function, and we covered that in 3.1. We also want to be able to say, I can determine if a function is injective, which we also covered in 3.1, and identify the domain and range. So we're going to dive more into domain and range here in section 3.2. So to define the domain of a function defined by an equation, we're really just looking at the input values. So we saw functions represented as kind of these oval blobs mapping from the first blob, which was the domain, into the second blob, which was the range. So let's do an example of that, right? So if we have ordered pairs, we could think about our domain as all of the x coordinates. So we've got 2, 3, 4, 5, and 6. And so that's going to be our domain. 2, 3, 4, 5, and 6. And what happens is that those get mapped into our range 10, 10, 20, 30, and 40. So those numbers make up the range. And we don't need to write any duplicates at all. So we've got 10, we've got 2 of those. We've got 20, 30, and 40. So what we see here is that our domain equals the set 2, 3, 4, 5, 6, and our range equals 10, 20, 30, 40. We're going to shift focus to finding the domain of a function. So here, instead of getting a list of ordered pairs, we have the relationship f of x equals x squared minus 1. So the domain is all the x values that we can plug into f. And then the range is all of the output values. So as far as values that I can plug into f, I can plug in any real value, because for any real number, I can always square it and I can always subtract one. So this is going to be all real numbers. And we can denote all real numbers in interval notation as negative infinity to infinity, or I can write blackboard boldface R, which is a type of typeset. The range is going to be a little bit different. So if we think about all the values that come out of this function x squared minus 1. So for example, is it possible to get negative 2? Well, let's think about that. If I had x squared minus 1 equals negative 2, all right, I might try to solve this using the square root method. So I'll add 1 to each side. X squared equals negative 1. Well, we know that the values that are solutions to this are going to be plus or minus I. But we're really going to limit our purview here to just real numbers, meaning numbers that do not have an imaginary component, numbers that are not complex. So how can we determine what the range is? We already know that negative 2 is not in the range. So maybe we could look at a graph. Maybe that will help us tell what our range is. So the graph of this function is just an upward facing parabola that crosses the x-axis at 1 and -1. Its vertex is at -1, and we'll go over this in greater detail later on when we cover quadratic functions. But really what you want to do is you want to think of the domain as all the possible x values that you could plug in. And you want to think about the range as all the possible y values that come out. And so we can see here that the lowest height is -1. But we have everything above -1 is going to be available to us here, right? Because these will continue upward and onward forever. So for this, the range is anything greater than or equal to -1. And so in interval notation, we would say that the range is -1, infinity, because we can have -1, right? That is on our list. It's not an open dot, it's a closed dot. So in example 3, let's just see if we can figure out the domain of this function. We're not going to worry too much about range right now, but the domain. So again, we want to look at what are all the possible x values we can plug in to f of x. And in general, the main kind of cardinal sin of mathematics is to divide by 0. So if we have x plus 1 over 2 minus x, the only thing we really have to look out for is not dividing by 0. So the only way I'm going to get a division by 0 is when the denominator equals 0. So let's figure out when that happens. So the denominator is 2 minus x, and that equals 0. Let's just add x to both sides. That's going to happen when 2 equals x. So this is the only prohibited value. So the domain is all real numbers except x equals 2. And the way that we'll write that is we can go from -infinity to 2, leave it open, meaning we're not going to include 2, and then we write this u for union to kind of pair it up with 2, infinity. So on a number line, what that would look like, if you recall from the earlier sections, we have 2 here. Let's see, we've got 3, 1, 0, 4, etc. These are our x values. What we're going to have is we just can't have 2, right? So I'm going to put an open dot at 2, but I can be over here. And this is 2, infinity. And I can also be over here. And this is -2, infinity. And so to put them together in a list, I just write this union symbol. And you should really think of that as the word or. So what I'm saying here is that the domain is all real numbers except x equals 2. So if I have the interval -infinity to 2, I'm okay. Or I could have the interval from 2 to infinity. So the takeaway here is that if we want to find the domain for a function that includes a fraction, then we want to eliminate the possibility of dividing by 0. So let's try it again here and try it number 3. So we're going to set the set the denominator equal to 0, because this tells us the prohibited x values, right? Because we cannot divide by 0. So if we know when the denominator is 0, then we know who to kick out of our domain. So we've got 2x minus 1 equals 0. We're going to solve for x. And we see that x equals 1/2. So the x value that I have to include here is going to be x equals 1/2. And what we'll get for our domain is everything but 1/2. So the domain is all real numbers except x equals 1/2. And I write that as negative infinity to 1/2 open, or 1/2 to infinity. There are other functions where we're going to have a problematic x value. So again, we want to focus on where our output is going to be real valued. So for the square root, just in general, the square root of a number is real if the number is not negative. So anytime we take the square root of a negative number, we're going to get a complex value. So we just need to make sure that, by the way, this is called the radicand. The radicand is the number or expression inside the radical. So we just need to make sure that our radicand is positive or 0, meaning that we need to have 7 minus x be greater than or equal to 0. And we can solve this inequality. So I'm going to add x to both sides. So I get 7 is greater than or equal to x. And this is our domain. If I wanted to write this as an interval, I would simply write seven as the largest possible value, and I can be 7, because if x is 7, then I'm having the square root of 0. The square root of 0 is 0. 0 is real. This is fine. And I can be as far negative as I want to be, right? So this is the domain. Let's talk about notation a little bit. If I say DOM of f, this means the domain of f. So in our case, negative infinity to 7 equals DOM of f, or the domain of f. So again, the rule here is that if we want to find the domain of a function involving a square root, we just need to make sure that the radicand is 0 or greater. And the way that we determine those x values is we set up an inequality. So let's try it one more time here with try it number 4. So remember, we want the radicand to be at least 0. So we set that up. We've got 5 plus 2x is greater than or equal to 0. I'm going to solve this inequality for x. So I get 2x is greater than or equal to negative 5. And I'm going to divide by 2. So I get that x is greater than or equal to negative 5/2. So as an interval, this means I'm at -5/2, comma, infinity. And I would say that the domain of f equals -5/2, comma, infinity. So next we're going to work on finding the domain and range from graphs. So again, the domain is all the possible x values, right? So anything on the x-axis that has an associated, that has like the graph that's right above it or right below it would be the domain. So there's something kind of hinky going on here, because on the left-hand side, we see that the graph stops at -5, right? X equals -5. We've got a hard end right there. But on the right-hand side, this arrow implies that this graph will kind of trend onward and downward to infinity. So the domain isn't all real numbers in this case. The domain is actually, we've got to look down. We kind of have to like project everything onto the x-axis. So imagine if you're standing above this graph and you're shining a flashlight on it, where does the shadow fall? And similarly, if you're below the graph and shining a flashlight on it, where does the shadow fall? Well, it's going to be all these x values here. And this is going to go on forever, right? So our domain is all of these values. So if this is the function f of x, right, given by this blue line, then the domain of f, which we write DOM of f, is going to equal everything including -5 all the way up to positive infinity. So that's going to be -5 to positive infinity. If we want to look at the range of f, now what we're going to do here is we're going to look left and right. So if we are standing at the side of the function and we shine a flashlight on it, what shadow does it cast on the y-axis? And we just consider all of those values. And so this is going on and on forever on the right. So for the range of f, right, which is all the possible y values, we can write that it starts at 5 and then it goes all the way down to negative infinity. So I would write that as negative infinity, comma, 5. And since we're including that endpoint 5, I'm going to give it the square bracket. So let's try it one more time here. Notice we've got a slight variation. We have an open dot on one end and a closed dot on the other. So this is a little bit trickier. So again, we want to look at all of the x values. I'm not going to include x equals -3 in my domain because I have an open dot there. So it's really going to be just everything but -3, and then we're going to keep going. And on the right-hand side, I am going to include 1 because I have a closed dot there. So the domain of f, right, again, if this is the graph of f of x, the domain of f equals open parentheses -3 because I don't have that as a point on my graph. that X value is not on my graph because I have an open dot. And I'm going to go all the way up to 1, but I am going to include 1 because it has a closed dot there. For my range, you might be thinking, oh, well, we're not going to include 0 because there's an open dot there. And that's true. But guess what? This point here on the graph at the origin is in the range. So that's what allows us to include 0. And then I've got everything else here. I'm going to include -4 because that's on the graph. And it's also here at this endpoint, appearing a couple of times. So we can see that our range is the closed interval from -4 to 0. So let's look at a more contextual problem. So here we've got a time series graph for crude oil production in thousands of barrels per day versus the year. So the domain is going to be all of the possible X values. But we're starting at, where are we starting at? I don't know. Let's call it 1973. So here's our domain. I'm including 1973. And I'm going up all the way to, let's say, 2008. And then the range is going to be all of the possible Y values. Oh, not quite that high, huh? So let's see. It's going to be everything from just short of 200. And then we have our peak here, which is just a little bit above 2000. And so our range is going to be all those values in between. We don't have any open dots to worry about, so my brackets will be square. So let's call it, I don't know, 175. And then maybe 2050 or something like that. I'm estimating visually, but it's just slightly higher than 2000 and slightly less than 200. All right, so next we have a bunch of toolkit functions. And we want to determine the domain and range for each one. So in the first example, we have a constant function. So here, this is the line y equals 2. The domain, we can see that it kind of goes on forever, right? So the domain is going to be just all real numbers, -infinity to infinity, or we might see that written as blackboard boldface R. The range, however, it doesn't really have a lot going on as far as height. In fact, it's always at 2. So the range is just the singleton, the single value, 2. I guess there's really no comma, huh? In our next function, we have a linear function, and we can see that the domain here, it goes on forever, but so does the range, right? It's going to go onward and upward to the right to infinity and downward and leftward to -infinity. So the domain is all real numbers, and the range is also all real numbers. Next, we have the absolute value. So we can see here that the range is going to be all real numbers again, but in this case, the only possible outputs are 0 or higher. So the range is going to be all non-negatives. The domain is going to be all real numbers. And this is exactly what's going to happen here with the quadratic as well. They're not the same function, but they do have the same domain and range. I can plug in any real number, but I'm only going to have non-negative output values. So my domain, again, all real numbers, range 0 and above. For the cubic, all real numbers, and the range as well, because this goes onward and upward and downward and backwards, or whatever the antithesis of that is. So my domain and my range are both all real numbers here as well. We also have the idea of this reciprocal function here. So looking at this, first of all, to notice is that the denominator cannot be 0. So the denom equals 0 when x equals 0. So the domain is all real numbers except 0. And so I write that as negative infinity to 0, union 0 to infinity. And then the range has kind of a similar story as well. So this was our domain. We can see here that the range never quite gets to 0. So I'm going to have all this stuff and all of this stuff, but I'm never going to have a height equal to 0. Why is that? Well, 1 over x equals 0, right? That's what I want to figure out. What x can I put in to make this function 0? Well, if I multiply each side by x, I get 1 equals 0. That's never true. So there's no possible x value I could put into this to make it have a height of 0. And so the range is the same as the domain. For the reciprocal squared function, it's the same as the reciprocal, except I'm squaring the denominator. So again, I have that if I want to figure out where I'm going to have problems, I set my denominator equal to 0. So x squared equals 0. And solving that, I get x equals 0. And then similarly for range, if I want to know when the height is 0, I would end up at the same situation, 1 equals 0 again. So this is never going to have a 0 height. It stops just shy. And the domain is everything but 0. So this is going to be the same as the example we just did here. The square root, right? So we saw that we couldn't have negative values in my radicand. So the domain here, I can have 0 and anything greater than 0. And then I see in my range, I can have 0 and anything greater than 0. Now, if I take the cubic root, the thing about a cubic root is I can put negative values in it. So for example, the cube root of -8 is -2, because -2 times -2 times -2 equals -8. So I can allow negative values here. In fact, I can allow any x value, and notice that I can have positive 0 or negative values as my output. So my domain and my range in this example are both all real numbers.